Why is embedded C optimization crucial for low-power devices? Imagine a tiny sensor sitting in a remote location, constantly monitoring temperature or humidity, running on a small battery. How does it keep working for months or even years without changing the power source? The secret lies in how the code running on its microcontroller is written and optimized. When you work with embedded C language for these devices, making the code efficient isn't just a good idea, it's a must. Embedded C is a popular language for programming microcontrollers because it gives you direct control over hardware. But if the code isn't optimized, the device can waste energy doing unnecessary work. For example, every instruction the microcontroller executes consumes power. If your code runs inefficiently, the processor stays active longer, draining the battery faster. Optimizing the code means it runs faster, so the microcontroller can spend more time in sleep or low-power modes. This is a big deal because most low-power devices relying on batteries that are hard or expensive to replace. Many microcontrollers have different power modes like sleep, stop, or standby. When your embedded C code is optimized, it can switch between these modes smoothly. For instance, if your device only needs to check sensors every few minutes, the code can turn off the processor in between. This reduces overall energy use significantly. Also, avoiding unnecessary operations like redundant loops or polling saves power. Instead, using interrupts to wake the device only when needed helps conserve energy. Another important aspect is how the code uses hardware features. Many microcontrollers have special hardware accelerators or built-in modules that can do tasks faster and with less power than software routines. Using these hardware features through optimized embedded C code can cut down the time the processor spends working. This means the device can go back to sleep sooner, saving even more power. Adjusting the clock speed and voltage based on what the device needs is called dynamic voltage and frequency scaling. Well-optimized code can help the system lower the clock speed when full performance isn't needed. This reduces power consumption without sacrificing functionality. Also, managing peripherals like sensors, displays, or communication modules carefully, turning them off when not in use, helps prevent unnecessary power drain. Choosing the right data types and arithmetic operations also matters. For example, avoiding floating-point calculations on microcontrollers that don't have hardware support for floating-point math can save a lot of energy. Instead, using fixed-point or integer math keeps calculations simple and quick. In real-world applications, these optimization techniques are used in battery-powered health monitors, remote environmental sensors, and wearable devices. They all need to run for long periods without changing batteries. By writing efficient embedded C code, engineers make sure these devices consume the least amount of power possible while still working reliably. To sum up, optimizing embedded C code for low-power devices is essential because it reduces processor activity, makes better use of hardware power modes, and cuts unnecessary calculations. All these steps help extend battery life and improve device reliability, making energy-efficient systems a reality in many electronics and embedded systems.